Chapter 2 actually starts with an interesting graphic showing an artistic representation of a technique called scanning tunneling microscopy. This is actually a technique where individual atoms are able to be visualized, and kind of serves as a good introduction to the fact that what we're going to be talking about, at least at the beginning of Chapter 2, is the proof and evidence that led to the theory that things and matter were composed of atoms, at least the proof and evidence for that theory. Now, the way this particular instrumental method works is we have a tip that is made out of gold that is very, very thin, down to the point where we have an actual tip of this probe that's only a few atoms across. A current develops between the surface and the actual tip of that probe, and that current is very, very sensitive to the distance between the tip and the surface. So you can use very sensitive electronics to measure exactly what that current is, and then keep that current constant by moving this probe up and down very slightly. So effectively, as you move across the surface, and this tip gets closer to a layer of atoms on the surface because that layer is closer or higher up on the overall surface, then what will happen is the instrument will sense an increase in current because the two objects are closer. It will adjust the distance of the tip, record the fact that it had to adjust the distance of the tip, and get back to the original level of current. So effectively what happens is you create this map of heights of a particular surface, and the resolution is high enough that you can see individual atoms in that surface. And let's take a quick look at a video to see how that works.
If the tip of the microscope is positioned very close to the sample, a current of electrons flows, which depends dramatically on the distance between tip and sample. Image acquisition by a STM. The scanning tunneling microscope exploits this dependence of the tunnel current on the tip sample distance to obtain height profiles of the sample. To this end, the tip is scanned line by line over the surface of the sample, and the tunnel current is measured. If the scanning tip encounters a step on the surface, the tunnel current increases due to the smaller distance between tip and sample. A sequence of line scans provides an image of the topography of the sample. Imaging atoms. The high resolution can be used to image individual atoms in the surface plane of the sample. We resolved the atomic structure of a copper crystal. Our images reveal that the copper surface can be modeled as a close-packed arrangement of hard spheres, which are spaced at a distance of 0.22 nanometers.
So keep in mind what you're looking at here is a scan that's actually showing individual atoms. All those little bumps are individual copper atoms on the surface.
Atomic manipulations. The scanning tunneling microscope is also a unique tool to create atomic structures on the nanoscale. The atom can be transferred to the tip and transported along the surface, moved with the tip to another position. Atoms can even be arranged in an arbitrary manner. This way, atom by atom, the letters MPI are formed, which is the short form for Max Planck Institute. This is a very small name tag. Its length is only 4 nanometers.